Hello and welcome. In this video, I'll show you how to use Altium Designer along with the Keysight Power Analyzer to analyze the power going through your printed circuit board. The purpose of this is to make sure that any board you're working with, whether high-speed digital design board or power electronics board especially, has the sufficient power it needs to operate your devices. You can get free trials to both of these tools. The Altium Designer primarily, of course, using my unique link in the description below to give you that free trial and also a nice discount to Altium Designer. So use the link in the description below. You may not get this discount if you don't use that one. After you've installed Altium Designer, you can go to the Keysight Power Analyzer, which is also linked below in this free trial button here, and it will take you to the free trial for you to try it out just like I am. This video is proudly sponsored by Altium. So next, let me show you how to set things up in Altium Designer. Okay, so once you've gotten your Altium free trial, you've gotten your Power Analyzer email with the activation key and everything, you're set up for your licenses. The next step is to open Altium Designer, log into your account, go to Extensions and Updates. In Extensions and Updates, you would go to the Purchased tab and then type in Power. The Power Analyzer tool will show up. Now, it doesn't show up for me because I already have it installed, but it'll be some icon and then you can click the Download or Install button here with this little down arrow. It will download itself, install, and then you need to restart Altium Designer to have it installed in the software. After that, you need to activate the extension. So you need to go to your account again, choose licenses, and right click on the tool, then choose use. Now you're in business and able to use the Power Analyzer. Okay, so the next step is to use the Keysight Power Analyzer. There's a quick start guide, which is also linked in the description below. And then if you go to the Spirit, this thing that's talked about Spirit, and you can do Control F and search down here, you can click on this thing that says modified version and it will download a ready-made board for you with some important changes. Now, if you don't want to do that and just want to work with your own design, you need to make certain changes to your design. So I'll show you exactly what those changes are. So let's say you have your own design opened up, right? This is this modified Spirit design. And you have a PCB, you want to analyze the power jack, the power coming through the regulation modules, and then how much is being consumed by your FPGA chip and by your LCD connector and whatever else. You can't just automatically analyze your board. You need to do a bit of changes in the design itself. So for our power sources, you need to click on the component or double click if you don't have your panel opened up on the right already, the properties panel, and that will open the properties panel when you double click it. What you want to add is this property called component type. So you need to go to add parameter, then you type in component type, then for the value you would choose source. This is a direct source of power. For your voltage regulator modules like these LDOs here, you want to click on the part or double click it to pull up the properties. Then you also want to add parameter and you'll type in component type. But for this, instead of source, just call it a VRM, which stands for voltage regulator module. Okay, so now that we have our power jack and our voltage regulator modules with the parameter value, we also need to define the power consumption being used by the chip and the current consumption being used by the LED. Current and power by the chip and current used by the LCD, excuse me. So let's go to the LCD part of the schematic. This LCD, we click on it or double click, and you would add a property with add parameter again, and then this time go and type in current consumption, right? Then you would say 18 milliamperes or 0.018 amperes. You don't have to put the unit letter, you could just type in the value. Then the FPGA chip, you double click on that and you want to add a couple of properties here, both power consumption and current consumption as shown here. Once your component parameters are set up, you also need to set your power nets. Here I've got a parameter set here. This is called your parameter set object. Then you would click on this and then you can make it small. So I'll just place it here and then click on this, double click. This could be large or tiny, and this is the tiny parameter set. Why would we use this? Well, you can go ahead and click add parameter, and the parameter you want to add is supply nets, voltage equals 5.000 or just 5.0. Then you also want to name your nets of interest, your power nets. Here, this is power underscore in or PWR underscore in. You can do that by just going to your net alias option, like net label option, right? And then you hit tab, then you would call it power underscore in and then place it on that net. You can also click on this icon and then place this bar. This bar will automatically name the net as well, and you can hit tab, give it the appropriate name, PWR underscore in, and then place it. Okay, so I'm not going to include all that. I'm just going to leave the example as is. Once you add those, you are golden and ready for setup. Alright, so our parameters are set up for our components of interest. Next, you want to make sure your PCB is mostly laid out, or at least laid out for the power that you are concerned about analyzing, but ideally you want it all laid out. Then go to Tools, Power Analyzer by Keysight, and you want to choose your configuration setup. For the configuration, you have things you can define like maximum current density for surface layers and internal layers, the minimum via diameter or the max current, the max via diameter, and all of these other options. I'm going to go with the default, but you can choose PCB copper or pure copper or custom kinds of copper. It's totally up to you. And then it lets you know what temperature we're operating at. You can also auto define certain settings like your VRM keywords and all that. I won't use the define automatically option. I'll just go with manage nets, and we're going to start building our power tree. Okay, so once configuration is set up, the whole trick is to analyze the power circuit by finding the sources of power, the voltage regulator modules included, right? So this would be our main power source coming through here, the fuse, the diode. We have the LED, the voltage regulator module. It's then taking that 5 volts and then providing 1.8 volts, 3.3 volts, and so on. Once we have our power sources defined, we need to define our loads, the things that are consuming power and current from our power rails. So we have R1 here. This will be included in the load list. We have LCD1. This is also drawing directly from the 5 volts. We also have the FPGA chip. This is drawing current from the 1.8 volts coming off of this LDO here. So let me show you how to set this up. In our setup, we go to Manage Nets. The net we care about is power in. This is coming directly from the power jack. We click OK. Now, let me show you something. Before I do that, if I go to Manage Nets, make sure your reference net is the correct reference net. Yes, so in this case it would be GND, and then we click OK. All right. Now we want to define our source. We'll click a source. This will be J1, our power jack. We'll click Save. Now, I'm not going to include F1. I'll show you how you would do extend nets to show that this fuse is connected in series with the J1, not as its own source. We'll click Save, then choose Extend Nets. Okay, and we'll include the fuse in there. Once we hit this plus sign, we choose the net that comes off of this power jack. Click Add. See, the fuse shows up automatically. We can say what the fuse is doing as far as voltage drop, resistance, max current, and all that. and you'd get that from the datasheet. I'll leave that as the default for now for 0. And then for this net, we'll extend this again. It automatically knows that 5 volts is on here. It goes to the 5 volts through this switch. The switch device, again, you'd go through the switch's datasheet, put the values in there that says it's max current, resistance, voltage drop, and so on. And now you have your 5 volts that goes to our voltage regulators. Click Save, and here are my 2 extended nets, my extended net here. Okay, now I need to add some loads. The first load I'll add is the LCD. So I'll click on the LCD. Now if I want to make sure that this is the correct LCD and it's actually connected to 5 volts, I'll click on my design item ID and it'll pull it up on the schematic immediately. Very nice. And we have the 5 volts here. So I'll click Save, and then it's the LCD. Alright, so I added my LCD, and let's make sure it's getting the correct input voltage. 5 volts in, not from the power in directly and not from the fuse net, but from that 5 volts that came out of that switch. It's connected to reference or ground directly through itself, its own pin. So we'll choose LCD1, which is itself. The load type is IC current, okay? And the load current we'll say is 0.018 ampere, which is 18 milliampere. You would define your minimum and maximum voltage that it can work through and through any data sheets that you would have for the LCD. Click Save, and now our first load has been added to the circuit coming off of that 5 volts, which came downstream from the power jack connector, the fuse, the switch, and the 5 volts. So that's how you add a load to your net. Next, let's add the voltage regulator modules to this power tree for analysis. These are technically loads, but they're voltage regulator modules coming off of that 5 volts. So the correct way to add these voltage regulator modules, even though they're technically loads, is to go to your settings. We'll choose manage here, and we'll add it as a load. So let's add U3. This U3, if we click on it, this will take us from 5 volts to 3.3 volts. So we'll click Save. And with the U3, I'll click on this icon and change this from IC current to VRM, linear. Voltage input is 5 volts and the output is 3.3 volts. The reference is ground, but how does it connect to this reference? Does it connect directly to it? Let's go and investigate. I'll hit Save for now, go into my schematic, zoom out, and this U3 is connected to ground through the R14. Okay, so I'm going to go back here, click on my settings, and this is R14 that I need to choose that it's connected to through to ground, because R14 is connecting to the ground. It's V out. I also need to update that to 3.3 volts. Now this stuff like R out, bias current, and everything, you need to get that from the data sheet. So let me show you a quick way to do that. I'm going to hit Save for now, go to Power, double click on this device. And if you have the design item ID or like the part number in the comment section, here's a cool trick. You can scroll down, choose Edit Supplier Links, click Add. It will automatically search the comment for the device information. You choose from your drop down here, you choose the one from DigiKey or Mouser Newark. I'll go with DigiKey because it's in stock. Click OK. And then I would just click on the device to make sure that this is the correct device. It automatically takes you to Octopart. Octopart, I highly recommend if you want to find any devices you're looking for on the web. It will have alternate components, replacements, replacement recommendations. You can add it to a bill of materials. You could find a datasheet at the source manufacturer's datasheet website. You pull up that data sheet and you can find the values you're looking for to add it into your power tree settings. Okay, I'm not going to do all that, but I just wanted to show you how Octopart really helps you like find all the information you need, including CAD models. See here we have the 3D CAD models and all that. Okay, so now that that's been added, I'm just going to go back into my settings, click on my settings icon, and then make sure everything is correct. Assuming I put in the correct values from the datasheet, click save, and we're good to go. Okay, so what happened here is we created a new mini power tree underneath this power in. See the top of this voltage regulator analysis tree, that J1 connector, it goes to that fuse and then the switch. Then its two loads are the two voltage regulator modules. We got the U3 and then, well, the two loads would be so far the U3, which is the voltage regulator module, and then the LCD, right? And we need to add another voltage regulator module, the U4, which outputs 1.8 volts. But I'll show you that in a bit. So click back on the PDN analyzer. We have a couple other devices that are on this main top side of the power tree. So I'm going to add those. Let's add R1 resistor. How do I know that I need to add R1? Well, let's go ahead and save this. Go into power, and I like to use the feature in Navigator. So go to the panels icon in the lower right, choose Navigator, and I'm going to navigate all the power nets in my design. I'm actually concerned about this R1 directly connected to my 5 volts. So I'm going to add this. And this fuse, I'm also wondering if this diode is consuming any power. Maybe just include that in there. It shouldn't really, so it's not necessary, but I might include this diode as well. So let's go into the settings again. And we're going to add these two loads, the resistor R1. This is a potentiometer kind of resistor. I'll set this at 20K. Click on the settings. Make sure it's connected to that 5 volts. Yes, and it is connected to the reference ground by itself. Yep. I want this VD1 as well. Let's add this. Go to manage. Click save. And this is coming off the net F1_2. So it automatically pulls up, well, I won't say automatically, but it includes this in the tree. So we just have to define, is it coming off the 5 volts, the power in? It's coming off this net here, coming between the power jack and the fuse. And then it's connected to ground through itself. The load current, we'll set it to something small like 5 milliampere. And I'll leave the rest the same. We'll click save. And that is our first section, our main top section, more or less done in terms of loads. Now, for my 5 volts to my 3.3 volts, I need to add some loads to this power tree. Go ahead and click save. And I need to start fleshing out my U3 part of the power tree. Let's look at show in tree. And let's see how this is set up right now. We've got our J1, yeah, the fuse, the VD1, that's good, that's correct. The switch, and then the switch goes to 5 volts. We've got our U3, R1, and the LCD. All right, that's looking correct so far. Let's go back into PDN analyzer. For this U3 branch, it has a number of loads on the circuit. So we'll go to manage, and then I will add multiple devices. If you check the schematic, you'll find that there, if we sort by designator, we have Y1 connected, U5 is connected, U6, and U1, they're all connected. So if you want to double check and make sure, you can click on it. See, U1 is the FPGA itself, and it's taking, it's drawing from 3.3 volts through some pins. U5 is also connected. It's connected directly to ground through pin 11, and it's drawing power from 3.3 volts. The U6 is also getting its VCC from 3.3. You can't see it since it's zoomed in a little too far, but likewise for Y1. So I'll go ahead, click save, and let me go in the settings here. It's coming off of 3.3 volts. That's correct. The total load current for Y1 Like, so you want to update those. It is connected to ground through itself. U5, double check that, 3.3 volts. I'll set this to 100 milliampere. It is connected to ground by itself or through itself, U5. Hit save. U6, go into its settings. I'll set this to 5 milliamperes only, and then it is getting power from the 3.3 volts and connected to ground by itself. And then U1, this is the FPGA. The FPGA has a number of pins, a lot of pins in here, and this will be around 800 milliampere current consumption, and it's connected to ground by itself or through itself. This is looking good. I'll go ahead, save this, and now let's see if the tree is built correctly. On this level, the 3.3 volt level, will show in tree. It's highlighted in purple, what we're showing. Again, according to our schematic, it should be J1 goes to fuse, right? If we go to J1, goes through the fuse, the switch, 5 volts, coming down. And I go in here, VD1, yep, 5 volts, coming down to the U3. U3 is supplying power to all of these devices. My 5 volts is supplying power to the LCD and to the R1. Now, there's one more thing. According to our schematic, the power jack leading to the 5 volts is also supplying power to U4, which is giving us a 1.8 volts on the output there. So let's go back into our settings, PDN analyzer, right? We need to add another load, that U4. So let's go to manage, U4 here. Let's click on that to make sure it jumps to that. That's good. Click save. And then U4 is not just a regular load, it is a VRM. Now, it's not getting power from power in, it's getting it from 5 volts. And its output is 1.8 volts. From the schematic, I had already noted that it's connected to the ground reference through resistor R19. Okay. And then the output volt, you need to change this to 1.8 volts. Then we'll click save. And now see, another color has been added. This load is a VRM, and another child of the parent. This is the parent. This is the voltage regulator module presenting another power child of the parent. And its load is the 1.8 volt section of the FPGA. Okay, which is U1. So its load, let me just double check to make sure, right? You can go to your panels, navigator. In the power section of your circuit, let's look at this 1.8 volts. What is it connected to? See how that FPGA showed up, right? See, that's getting that 1.8 volts. So now we'll go back into our settings. The U4 and the load is the U1. So we'll click on here. U1, click save. Now we did say that the current consumption could go up to 1.65 ampere. That means we have 800 milliamperes coming through the 3.3 volts, and from the 1.8 volts we can have another 850 milliamperes. Those two combined will add up to 1.6 ampere. So let's click on the edit option. Make sure 1.8 volt is chosen this time for the U1. You can connect it to the ground through, it's directly connected to ground through itself, U1. And then here, we'll set this to 850 milliampere. Okay, and then we have the minimum voltage and max voltage defined. You'd get these again from the data sheet. We'll click save, and we are good to go. Now, let me double check, show in tree, it's highlighted in purple. The tree is saying that J1, the fuse, VD1, the switch, we're outputting our 5 volts as shown in the schematic earlier to U4. U4 outputs 1.8 volts. to the FPGA, excuse me. And then the U3 is all the voltage regulator module, which provides 3.3 volts to U6, also the FPGA, U5, Y1, so on and so forth. And we have our direct resistor connecting from the 5 volts to the ground, and then the LCD also drawing some current from that 5 volts. So this is the proper power tree. Now we are ready to simulate the power consumption in the printed circuit board. Now that everything's set up, it is the moment of truth. Let's go ahead and analyze all nets. It's simulating. And then it'll let us know what has failed and what has passed. So see in this top PDN, it has failed based on the configuration settings we have here. Maximum via current, it's been exceeded. Current density is fine, voltage drop is fine. And voltage drop refers to our DC drop limit here. You can set it to a custom amount. You know, we have to be very careful about the voltage drop. We don't want it to drop very far. See, we have all of these options here. Failed. Now these passed. Our maximum via current got pretty close. But let's take a look at this on the PCB. So let's show on PCB. And see, we get this nice graphic, this visual that shows us what's going on among these, along these traces. Now, only after you've chosen show on PCB and ran your analysis does a panel show up called the power analyzer by Keysight. It's only in these conditions. So if you chose via current here, see, we can look at violation types via current, and it will let us know, and it'll pull us right in there. And you can choose from your drop down your power net. What power net are you concerned about? You can also check mark any nets that we're only concerned about that has violations. You can uncheck this, and then it'll pull up the rest of the nets to let us see those nets, right? Let's say we only care about violations, right? And you can show a heat map, or you can not show a heat map. But let's show the heat map. And then we can analyze again, depending on, like, if we change something on the routing, and it will show us. Okay. Very wonderful. Now, this is a problematic, and let's say I want to put this in a report. So I would bring this up, click add, and this captures a picture of this right here. Okay, so I'm capturing photos from my report. If I click on heat map on this tab at the top, I can show arrows of current direction. We have current circulating along here, along this trace. Let's see, what's my current flow looking like over here? Yep, all that current is going into that via. Okay, so if anyone's curious, what's the current flow in some arbitrary area, you can let them know. Now, if you want to choose the hotspots automatically, you can choose use logarithmic to see where the hottest or the highest current density is automatically. Then you can zoom in and then uncheck the use logarithmic, and then you go with your linear again. Okay, you can also look at voltage drop. Instead of just for current density, you can click on voltage drop, and you can check whether the voltage is dropping by voltage or percentage. Okay, you can even modify your slider here to see what voltage drops we care about. Okay, you can enable visual slider for a voltage contour and add specific points to your contours that you care about. But I'll go with current density for now. In fact, you know what? Let me take a photo of this. Go to general, and I'll add a picture of that voltage. And what's cool is I can choose the layers where I want to see my results on. So that was the top layer just now. I want to add this bottom layer to my report. Okay, that's looking good. Now that's the power in net. What about my fuse net? See, this is a problem here. Okay, I'm going to take a picture of that. Okay. Now, what about nets that don't have violations? I just want to see what's going on with this 3.3 volts. Okay, we've got some hotter spots in these areas for my 3.3 volts, right? And you can add your image capture there. Now, as you would have seen here, this got cleared for my previous images I had chosen, but that's fine. You can go back to your net and it will still have them. Okay, so we'll go to our 3.3 volts. That's on the bottom layer. The top layer, I see, what's the consumption by the chip, the FPGA. It's looking fine for the most part, right? So we see graphically, visually how it has passed the test. And on the 1.8 volts, what's the performance like here? Yeah, so we've got slight hot spots around here. I will add this picture. I might want to probe a specific area. So if I want to probe, I can click add and then click on this spot and this spot and see what the voltage difference is like. So 1 millivolt drop, that's fine. Maybe I don't care about that though. I care about what's going to happen for the voltage drop from this point to maybe over here. 11 millivolts, see. Depending on your application or your design, maybe that's a little too much, like it's bordering on a little too much if you're working with really low voltage. So this is why the Keysight analyzer is so useful. Let's click save for everything, and there you go. So I have all the information I need. The next step is to generate an analysis report. So to generate an analysis report, I'll go back to my Keysight document. And I'll report this to the PCB layout designer or the manager, and then we'll do some kind of design review to see what improvements can be made. So click View Full Report. And here you can click on any of the nets and it will show you the report for that net. It will show you where it failed, the bottom layer, the top layer, heat maps for your voltage drop, the system level power network results. Seeing your system level power tree like this will let you know if there's maybe even a problem in the schematic design. You'll get to see least margin, margin types, list of violations, and the failed via summary. This is very nice. So you can see from testing and simulation before you get your board out whether your vias are sufficiently sized or not. And not just sort of guessing based on best practices for vias. This is even the PCB stack up. So let's say you loaded the wrong stack up. Seeing everything all in one place lets you check and double check things that you might have missed. Here's the full report. You go back in here, the 1.8 volts section of the report. It lets us know, see, it shows us everything again, making sure that we're in the right sections. Okay, so I'll go ahead and save this report. I'll choose everything and generate the report. Then it creates this wonderful report that's HTML format. You can double click on it and share this with anyone in the organization so they see everything that has the parameter, the right settings. Maybe you can ask your manufacturer if they have certain materials, like what their materials are, what conductivity their metals have, or you can use this to specify what you need in your design and then choose the manufacturer that can meet those needs. Okay, this is a wonderful tool. It's comprehensive, it's useful for high-speed designers, and also once you're done with your design, making sure that everything has passed your test, you've updated everything, then you can go into your PCB project, export your files, like your Gerber files, your ODB++, because now you're confident in your power electronics design. So you'd upload your files, put them in this Altium free viewer, or the files directly. Anyone else can look at the PCB layout and they can focus on manufacturability, assembly. And that's not just for Altium designs. You can do it for Autodesk Eagle files, Gerber files, KiCad, okay? Alright, so I would highly recommend the Keysight Power Analyzer tool. It's extremely important, really, for high-speed design, power electronic design especially, and just in general for any PCB. Now, if you're not sure about the full process to hardware and PCB design, to go from start to finish, and you're just focused on PCB layout and analysis, then you want to check out my next videos where I explain the different aspects and how to step through an entire PCB design.